do this. So this is the mic going through Zoom? Yep. Okay. Good. All right. We're good. Okay.
And we have a stick in case you want to point.
Oh, great. Okay. And do you want me sharing the slides on Zoom?
Oh, yeah,
Yeah. Okay. That will take me a second.
that's. I mean, that's the reason why.
Yeah.
We're looking to Zoom yourself.
Okay.
Let's see. What we like this. No, there's a. You're.
It only looks backwards to you. Not to anybody else.
Really?
Yeah, because when you sort of move left or right, it's easier to do. Good, so Zoom has software that on your own camera,
It looks backwards to you too.
so the others.
Yeah.
are-
Okay.
It's good, it's good.
Wait a minute. What's in my column? Yes, I. But, you know, sometimes you have to take double takes. So there is a question of philosophy of what to do with a camera back. Because we have it on Zoom, I feel like we should show the room. So the people on the.
Yeah, but once I share, it'll just
Right.
It'll
right,
dominate,
that's what I'm
right?
saying, trying to get the big camera to point, I think the room is more important, the vibe.
Yes, we will. I can share one or two stories.
Oh,
Just make it.
oh,
Unfortunately, they don't have a partial. Is this okay, or is this too much? I don't want that.
That second one, where there was something back here, but this will do.
and if I need to use the whiteboard, I can just turn on the light.
Yeah.
When it
that's the
happens,
first,
yeah.
First flip.
Okay.
Does anybody want to? Oh, wait, one thing that we have to deal with was.
I can get rid of it.
Yeah, if you can get rid of it.
Yeah.
Right.
Yeah.
Oh, okay.
No, I don't need to. I can just start. It's okay.
Okay, so our first speaker is, I'm probably gonna mispronounce your name.
Give it a try.
Chitamber, right?
Chitamber. Chitamber, yeah.
Okay.
It's close enough though.
From the University of Illinois, Champaign-Urbana. And he is going to tell us about, and actually our next speaker will too, about some extremely interesting work going on in network non-locality, just kind of an extension of Bell's theory of ideas to the networks. So I'm definitely interested in hearing what both of them have to say.
Great. Well, thank you, Mark. It's a pleasure to be here, and I'm going to just from the get-go, let me just thank all the organizers and everyone here who I've had a chance to speak with. Unfortunately, I will have to cut out in the middle of the next talk, so I won't be saying goodbye. So this is my goodbyes here. It's just for some family matters. I have to get back home. So what I'm going to talk about this morning, indeed, is this notion of quantum non-locality in networks. And this is an active and I would say relatively new area of research. And I think it will also feed into the next talk as well when Ellie speaks. So what I'm going to do is basically start from the beginning. And I don't know all of your backgrounds as far as where you are scientifically. So what I want to do is kind of unpack this slowly. And I've structured this talk into 4 parts. So first is just a general introduction to Bell non-locality. So before we get to the network setting, I want to make sure that everyone is kind of on the same page and understands this notion of what we mean when we talk about Bell non-locality. Okay, so this will encompass a good chunk of the talk. Then we'll move to non-locality on multi-party networks. Okay, and this is now where we're going to see some new phenomenon emerge that we don't get in the standard Bell scenario. I'm going to specifically focus on a class of networks known as the bilocal networks, and also their extensions to entanglement swapping networks, or essentially is just a repeater chain. So where you're doing entanglement swapping along a line. And then I'll have a bit to say about actually the type of operations you need to generate different types of network non-locality. Okay, and so when I say different types of network non-locality, I'm getting into definitions, and I've been told that next talk will take a deeper dive into sort of the definitions in classes. So again, this should provide a good segue into the next talk. Okay, and I'm just going to give some references up front here. These are 2, I think, excellent review articles on the topic. So this is a kind of a standard reference in the field. This is Nicolas Brunner's and co-authors review on Bell non-locality, which is now almost 10 years old. And Armin Tavakoli's and co-authors their work on specifically network non-locality. So both these I think are very readable introductions. And so I'm going to kind of be moving in between the space of those 2 articles. So for further reading, I point you there. Okay, so let's begin from this starting point of Bell non-locality. And by the way, I'm kind of thinking of this as very, I don't want to say informal, but more of a tutorial style talk. So please, at any point, stop and we can have a discussion, or I can kind of clarify a point in greater detail. All right. So in the study of Bell non-locality, at least in the modern formulation of it, we usually think about things in terms of black boxes. Okay, this is kind of the easiest way to visualize or isolate the particular phenomenon that we're considering. So when I say a black box, it's something like this. This is a very famous picture you'll see if you read most any paper on non-locality, where you have Alice and Bob who are just agents and they have classical variables. X and Y is the input to their black boxes, and they have A and B as their outputs. And when I say black box, what I mean, for the moment, we're not going to have any consideration about what's going on inside the box, right? How you're mapping from X to A as far as physically how this is occurring. I mean, indeed, there will be some physical process under the hood, but we want to kind of maintain a process agnostic perspective for the moment. And we just say, all right, well, there's these black boxes. They have some inputs and they have some outputs. And we can then explore these boxes, and we can then study what their joint behavior is. All right. And this is the joint behavior then is just described formally by some conditional probability distribution, right? So if they input X and Y, then they can observe the frequency of getting out A and B. And so then they can form the sample average and infer a probability distribution. And so actually you can already see I'm making some assumption here, right? I'm making some assumption that these boxes are memoryless, and so that there's some statistical frequency here that you can actually infer. So if you repeat this thing, it behaves the same, right? Okay, but nevertheless, I think if it's just a black box sitting there, you can assume that under each performance, it's sort of behaving the same way. And so we're going to make that assumption. And what's cool about these boxes now is that in our model, we will assume that they behave the same way regardless of where they are in space. Okay, so you can take these things and you can separate them very far apart, and you would observe the same input-output behavior. Yeah. And again, this assumption I just mentioned, that the input-output behavior is the same regardless of how many times the box were used in the past. So there's this memoryless assumption going on here. Okay. Now let's add a little bit more to this. So I mean, this is interesting. They have these devices, and actually, I'll take one step back, and I'll say I think like this model is very good for understanding almost anything we do in life, right? You can think about like life as a black box, and you have some input to your black box and you get some outputs, right? So if it's like trying to trying to get my kids to do some job, right? So I have some input to this box, the way I speak to them, the incentives I give them, and I get some output. And I see this many times, I find which strategies are successful, which are not. Yes.
So should I think of these boxes as a dynamical system that's indestructible, that there's nothing I do to the box that it's.
Yeah, just right. Yes. Yes. Yeah. If you want to bring that in, then that would be something different. But for now, just keep it indestructible. Yeah. Okay. All right. Good. And so now we are going to add a little bit of a flavor to this, and we're going to assume that unbeknownst to Alice and Bob, in fact, there's some common source of side information feeding into these boxes. Okay. So again, all they're seeing is the input data and output data. But there could be something going on that's actually connecting these boxes. And I'm an information theorist, so I like to think of this in terms of side information, right? It's really just you have access to one particular random variable. You say your output variable here, but that variable is correlated to something else. All right. And so that constitutes side information. All right. So now this is getting interesting because we can ask this fundamental question of how do different types of side information change the input-output behavior that these boxes can generate? Okay, different types of side information. So what do I mean about different types of side information? And I'm here referring to like 3 different types we could consider. So one would be that the side information is represented by bits, strings of 0s and 1s. And so this would be some classical information that's being fed into the boxes. But okay, this is a quantum networks workshop, and so you could imagine that in fact you're feeding qubits into these boxes. So this would be some quantum side information that's going into the boxes. And you could push this even further and say, well, maybe you have something that's stronger than quantum mechanics, or something that we can theorize. We don't really know if nature behaves according to these rules, but we can always just get creative and come up with some new objects that are neither classical or quantum. And in fact, this may be feeding the boxes or correlating the boxes. Okay. So this is actually a very it's a cool paradigm because it allows us to probe different theories of nature. Just by considering different types of side information, we can study how that affects the input-output behavior of these boxes. So I like this paradigm quite a bit because it actually gets to some fundamental questions and allows us to make separations between different physical theories of nature. Okay, and so that's basically what we're going to do in this talk, is explore this. So first, let's look at the case of bits being distributed. So I will refer to these as classical boxes because you're feeding bits into the boxes. And this is also known as the locality paradigm. And you'll see a reason why it's usually referred to that. And here, this side information is shared classical randomness. So there's some random variable lambda, which again, we think of as strings of bits. And there's some probability distribution over it, p lambda. And again, this is not known to Alice and Bob. So if they're just to describe the input-output variables, they would have to go down here. They would need to average over, right? So this is the joint behavior here. But there's one thing here is this notion of locality, and it's this condition, which I skipped over. But it says the following, that if you're given the input variable, then the output of the boxes, they behave independently. So basically, once you have this variable lambda known to Alice and Bob, then you get independent behavior of the boxes. And this condition is sometimes referred to as Bell locality, because you're sort of able to localize the behavior of the boxes into two independent devices there. Okay, and then when you average over this unknown variable, if you make the assumption that in fact these inputs x and y are independent of lambda, then in fact you get this joint behavior. It looks like this. Okay. An assumption here: the value of lambda is independent of Alice and Bob's inputs. So what that means is that there's some sort of free choice going on here between Alice and Bob that's uncorrelated from this lambda. Right. And again, from an information theory perspective, it's a very easy and natural assumption to make. You just say you have two random variables that are uncorrelated. Okay, so their joint distribution factorizes, and so you get this. All right, but you could consider relaxing this assumption. In fact, in some of the loopholes, or if you've heard of these loopholes for Bell tests, one of the loopholes involves, in fact, not requiring this. Right, so you have some dependence between the random variable lambda and then the input choice is there. Okay, so if you want to close all your loopholes in your bell test, you need to address this question. Okay, so these are the classical boxes. Good. Okay, and now we can move on to the quantum boxes. So remember, the quantum boxes is now we're distributing quantum information in the side channels. And so it looks like this. The most general thing I could do is prepare some entangled state and then feed it into Alice and Bob's boxes like this. Okay, and the way you should think about this, if you haven't seen this before, it seems kind of it might seem very strange. I'm going slow here just to hammer in these concepts. But you see, if you just look at any of these boxes, you have two things going on. You have a quantum input and you have a classical input. These are the instructions that Alice is feeding her box. And then you get some classical output. So you should really think about this as being some mapping from which we call a CQ state. So it's a classical quantum input and then to a classical output. But really what's happening is that in order to get this classical output, you're making some sort of measurement inside the box. And the choice of measurement is determined by this classical input. So I refer to this as instructions a lot of the times because it's telling Alice or Bob how they should measure their quantum system, right? And this is a unique feature of quantum mechanics. The fact that we can make different types of measurements on our system, right? Well, you heard about perhaps BB84, right? So you can measure in the 0-1 basis or the plus-minus basis. So I have some freedom in how I can probe my quantum system. And that's described by this classical input here, so that allows me to adjust the way that I measure my quantum input, and then I get some classical output. Okay, so that's what's going on here when you see these quantum and classical arrows pointing into the box. Okay, good. And so then we can easily compute the behavior of these boxes just using Born's rule, right? So this Born's rule says the following: that I have some measurement operators associated to Alice's measurement and some associated to Bob's measurements. And so then this is the shared state that's fed to them, and then they can just compute the probability by this inner product. Okay, so this is just quantum mechanics here. So we're really just applying, what you learned in your quantum mechanics course. All right, and so these therefore are called quantum boxes. So quantum boxes are boxes you can build in this using this model. So you distribute an entangled state like this, and then you perform some measurements. All right, so now we can formally define what this quantum non-locality is. So when we're talking about non-locality, we're talking about non-classical quantum boxes. That means that they're boxes of this form, right? So I'm building them using some quantum model, but they're not able to be built using classical shared randomness. Okay, so using the model where we have bits that's distributed. Okay, good. How are things so far? Is this kind of too basic for you guys, or is the level okay? Level's all right? Okay. All right. One other piece I want to talk about in this puzzle. I'll go a little bit faster here because we're not going to dwell too much on this. But there's also, as I mentioned, you could get creative and come up with theories of nature that go beyond quantum mechanics. And one would be a theory where you're just limited by special relativity. Okay, so in special relativity, what's kind of the golden principle there? The fundamental rule is that you're not able to send information instantaneously, right? There's some finite speed limit to how fast information propagates across spatial distances. All right, and another way of saying that is sometimes called non-signaling. And so what that means then is that Alice is not able to communicate to Bob. Remember, Alice and Bob could potentially be located as far apart, right? That was the assumption we made in the setting on the different opposite ends of the galaxy. So whatever Alice inputs here should have no effect on Bob's output here. Otherwise, there'd be a communication channel from A to B, and likewise from B to A. All right. But there's a kind of a cool middle ground between uncorrelated boxes and communicating boxes. All right. So there's ways that you can generate correlations that aren't communicating, and that's what this non-signaling box does. I'll give an example a little bit later. But it's just some other, for the moment, just think of this as some sort of side box that they're using, some device that they're using that allows them to correlate the behaviors of their individual boxes in ways that doesn't allow communication. If you wanted the formal definition, it looks something like this. So if I just look at Alice's output, so I'm marginalizing over Bob's output B, this should be a constant for every A and X. So as soon as Alice chooses her input here, then what she sees here statistically should not depend on Y, and then vice versa. Okay, that's the formal definition, if you want, of non-signaling. Would look something like this. Okay, and so quantum boxes are non-signaling, right? Quantum mechanics has this nice consistency with special relativity, which you can just obtain from this definition. So indeed, if I have a quantum box, it looks something like this. And if I marginalize over Bob's outputs, then I just get a nice fact that because my measurement operators must sum up to the identity, now I have no dependence on B and Y here. So this is going to be some constant for every A and X. Yeah, good. Yeah. Yeah, go ahead.
I just want to make sure I understand the notation. The usual
Yeah.
probability is psi squared. In your notation, psi would be of the product.
Yeah, yeah.
Where's the?
Yeah. Okay. Right. So it is a psi square. So
It is.
I'll write here because I can. So I have trace. So my notation is this. When I write psi AB, I should think of this as an outer product,
Got it. No,
right?
no,
Like
that's
this.
fine.
And so then
That's
I
fine. That's
get,
fine.
yeah. If it were a density matrix, I mean, then it would you just plug that density matrix in there. Yeah. Okay. Good. Thank you. All right. Okay. So why study these non-signaling boxes? Okay. So first of all, I give a couple of reasons. One is that I think it's kind of cool. Again, you can get creative. You can ask questions like, well, why isn't nature more non-signaling than it is? Why are there these limitations to quantum mechanics? What if we had a bit more computational power that go beyond quantum mechanics? What could we do with that, right? And Anne has done some work on this. Others have done some work. It's a cool question, and so you're sort of studying computation, security, information theory from a more physical perspective, and try to understand the interplay between the laws of nature and what you can do from a computational information perspective. So I think that's a very kind of fundamental reason for studying this. Another, maybe more practical reason is that you see we're able to simply write down these non-signaling conditions. All right. So this is nice because this gives us a set of algebraic conditions that we can work with. And a lot of times it's easier to analyze these algebraic conditions than it is to analyze the conditions for quantum boxes. So it gives us an outer approximation for something we can do quantum mechanically. And usually this outer approximation is easier to compute than if we just try to try to compute whether or not we can do something quantum mechanically. Okay, so I'm giving a mathematical explanation or defense for why we study non-signaling, is that it gives us kind of a simpler relaxation to work with. Okay, good. So a nice way to think of this and kind of summarizing the points that we've talked about so far is to show our boxes geometrically. So suppose that your inputs, say, go from 1 to Dn, and our outputs are chosen from sets 1 to D out. So these are finite input outputs. Then we can take our transition probabilities for our boxes, and we can form a d-dimensional vector, right? So I'm just think of this now as a vector, and these are the components of a vector. So a, b, x, and y. So that's the product of all the variables, right? So I'm forming this big vector. And now what I want to do is I want to place this vector in real dimensional space, right, in RD. Okay. And so every box that we've encountered will correspond to a different vector in this high dimensional vector space. Okay, cool. So now we can think about ways of formally defining subsets of RD to characterize the different types of boxes. So first one we have is just if these should be valid probability vectors, right? Meaning that for every x and y, the a and b should sum up to 1. They should form a probability distribution. And also the elements should be non-negative, right? If these are really probability distributions, then there's certain constraints this must satisfy. So that will already kind of isolate a particular subspace, or rather it's a convex set of RD subset, right? Okay. And now you could ask about these non-signaling boxes. That's going to form an internal subset, convex set to our probability vector space, right? So these are boxes that satisfy those non-signaling constraints that I wrote down in the previous slide. Included in that are the quantum boxes. These are boxes that are built using shared entanglement, right? And then inside that then are the classical boxes, which are built using shared randomness. Okay, so again, any point in here then corresponds to a vector of probabilities, which then corresponds to a physical model. All right, so I want to just remark on a couple geometrical features. So first, the probability P here. This is a convex set, and it's a polytope, meaning that it's you can write everything as the convex combination of some extreme points. And I think this picture is suggesting that, right? So I have my vertices here. The same is true for the non-signaling boxes, right? So this forms a convex polytope in space. On the other hand, the quantum boxes, while they are convex, they don't form a polytope, right? So they have kind of this smoothness to them. And then the classical boxes also form a convex polytope. All right. Yeah. So I can write, okay, so it's a subset of real space in which I can characterize a subspace as a convex combination of a finite number of extreme points. So convex combination means that I can choose extreme points. So look at P here, right? So I have 1, 2, 3, 4, 5, 6. And now I look at all the line segments between all these extreme points.
Is there a physical significance to these extremes? These points don't come from some balance. They're actually
right. These come from, so the physical significance is this. These correspond to deterministic boxes. So what I mean is that when I put in inputs, with probability 1 or 0, I'm going to get an output back. So there's no sort of uncertainty in it. Right. The uncertainty comes when you kind of mix strategies and you interpolate between the extreme points. Yeah. Okay, great. Any other questions? All right, and I bring this up because when we go to network non-locality, this beautiful picture is going to go away, right? And so we lose the convexity, and that's one of the big challenges in dealing with this. Yeah, go ahead. Yeah.
I think I roughly understand quantum mechanics, but perturbing from quantum to the more general non-signaling box.
Yeah.
Is there any kind of intuition for modeling? Kind of like what kind of models of communications are beyond quantum?
I'll give an example. Yeah.
All right.
An example of this. I don't know if it'll be satisfying, but so we can come back to that. All right. Good. Okay. So now when we have this geometrical picture, it lends itself well to what are famously known as Bell inequalities. Okay. And the reason is that you see, when you have any convex subset, in fact, any polytope like C, what you can define are hyperplanes, right? That tightly bounds your set. Okay, and so what are hyperplanes? Well, they're just formally they're just some solution set. So I have some constant C, and this is just like a linear equation. And so what I have is for every hyperplane, I have a linear equation that's defining this. And so the points on this hyperplane are solutions to this equation here. So beta is some fixed constant and C's are other fixed constants. And I ask what are the solutions that lie that solutions to this equation, and they form then a hyperplane in this higher dimensional space. And so a fact about polytopes is that in fact you can characterize the polytopes as the intersection of a finite number of hyperplanes. So in C here, for instance, I have a hyperplane here, I have a hyperplane here, here, and here. And so that tightly characterizes C, right? The common space that's internal to all of them forms this set C. Okay, and in the field, then we refer to these separating hyperplanes as Bell inequalities. Okay, but mathematically, you should think about it this way. Okay, it's just a way to separate your classical set from the non-classical objects. And this is extremely useful because it gives us a condition for membership in C, right? So if your box sits in the set C, then it must lie on this side of your hyperplane. And so over here, right? So you can formally characterize over here by an inequality. So beta is, when you're equal to beta, you're right on this line. When you're greater than beta, you're on that side. And when you're less than beta, you're on this side, right? And so if you're in C, you're on the other side of the tracks. And so then you must satisfy this condition. Okay. So what's useful about this is it gives us a way to certify that you're not in C, right? If you violate this inequality, then in fact, the boxes Alice and Bob have don't belong to this classical set. So then they exhibit non-locality. Right, and indeed, this is the philosophy approach that's taken to certify in the laboratory that you actually have some sort of non-locality present in your experimental data. You show that you violated one of these inequalities. All right, and the most famous example of this is what's known as the CHSH inequality. And so this considers boxes with just binary inputs and outputs. So Alice and Bob each have a bit. Right? And this inequality looks like this. All right, so again, it's just some linear equation on your probability points here. And so you need to be bounded between -1 and 0. This will give you like 2 hyperplanes that constrain your classical set. Okay, so if you can build boxes that violate this, good. Then you know that it can't be built. Then there's no classical model that indeed generates the behavior of those boxes. So there must be something quantum going on. There must be some quantum entanglement that's been distributed to Alice or Bob, right? Or one of these loopholes or the assumptions we've made are being violated. Okay. All right, and I give one inequality here, but in fact, you can get more just by relabeling. So here I've switched the inputs. I've done a bit flip here, and so you can generate a whole family of equivalent Bell inequalities just by doing some relabeling here. Another way of expressing this, and this is kind of the more common way of writing down the CHSH inequality, introduces what's known as correlation functions. Right, and we'll see these later in the talk as well. So a correlation function is just the following. What it's doing is whenever you have Alice and Bob have the same output, then they get a score of 1. And whenever they have opposite outputs, they get a score of -1. Okay, so this is just determining the parity. Okay, and so then you look at the average score, the average value that they have. Right, so you're adding together the outputs when they're the same, and then you're subtracting the probability when the outputs are different. Okay, and that's what's known as the correlation function for those two. For Alice and Bob's X and Y inputs. Okay, and so it turns out that in fact you can express this CHSH inequality in terms of these correlation functions, and it looks like this. And this is the more, as I said, this is the more common way of seeing CHSH. And if you do like a Wikipedia search, or if you open up most standard textbooks, you'll see it expressed in this way. All right, but seeing that this is a workshop, I thought it would be good just to leave this as an exercise for you guys. To move from 1 to 2. Okay, so we won't go over it, but it's a good way to understand that you have a sense of what's going on here, right? So indeed, prove this correlation expression for the CHSH inequality, starting from just the probability description. Okay, homework. So what does this look like on the geometrically? So it would be, again, the CHSH is some sort of hyperplane like this. All right. And well, we can go beyond that. And so using quantum mechanics, we can break the CHSH inequality. And so there exists a quantum box that can go 2 square root of 2. Right. And the strategy goes like this. Alice and Bob share an EPR state, a maximally entangled states. And then Alice measures uses sigma z or sigma x. These are poly z or poly x. So on the block sphere, she's measuring in the z direction or in the x direction. And then Bob measures in a direction that's rotated by 45 degrees. So he does one measures this observable or that observable. Okay, and you can go through the math, and you can show that it gives you a 2 square root of 2. All right, and now to your question, what kind of goes beyond the quantum? So there is a non-signaling point up here, and in fact this is tight with the probability polytope because it's the largest possible you can get over if you just demand that you have a vector that satisfies a valid probability distribution, and so you can get a score of 4 here, right? Because each of these are bounded between 1 and -1. So the largest possible value you can get here is 4, and in fact you can get it using a non-signaling box. This is the most famous non-signaling box. This is what's known as a Popescu-Rolich box. And it's just defined by this simple rule here. So it's everything is you either have outcomes are given by either 1/2 or 0. All right, so they'll just look like coin flips. But the point is that Alice and Bob's outputs will be correlated, meaning they're the same. They're either 0, 0, 1, 1. Whenever they don't put in values 1. Okay, so if one of them puts in a value 0, then they'll always be correlated. If they both put in 1, then they'll be anti-correlated, meaning 0, 1, and 1, 0. Okay. And so you can check then that this gives you a point outside of there. All right, and I to maybe answer your question a little bit deeper. You know, there's a lot of work going on to explore this area between Q and non-signaling. You know, that would be a kind of a seminar in its own.
Yeah, I think I was wondering more about kind of like more hands-on intuition for how to design a non-signaling box.
Okay, right. So yeah, okay. So if we believe that you can't leave this physically, right? So then how would you actually realize this? So the way you would have to do it is you would have to relax one of our assumptions that we've made. Okay, and one of those assumptions is that you're able to actually communicate between the two boxes. So what you could do is you could simulate a non-signaling box by having some information leak from Alice's lab to Bob's lab. And so then you don't have this scenario which I described where they're completely separated across the galaxy, but there's some sort of communication flow, right? And it could be noisy, and if it's noisy enough, then indeed you're able to simulate the statistics of a non-signaling correlation. Yeah, that would be one way of doing it. Okay, good. I want to make a point here. So boxes without inputs. So in the CHSH scenario, there were 2 bits for Alice and Bob. So they chose between 2 different measurement directions to make on their system. But now I ask the question, you know, what about boxes in which one of the parties has no input? Right? Okay. And the question now is it possible to build quantum non-local boxes if one of the parties doesn't have an input? So what I mean here is that are you able to find a separation between the set Q and the set C if say Alice doesn't have an input? Okay. All right. Well, the answer is no. Okay. And again, as another exercise, I want you to I'm going to give you like 10 seconds just to kind of think about this question. Or how would you prove that in fact every non-signaling box can be built using classical randomness? Right. Maybe just make sure you're understanding what is being said here first. So it means that if I gave you any box like this, which is non-signaling, and so non-signaling here would just be strictly from Bob to Alice, because Alice doesn't have an input, so there's nothing for her to signal to Bob. So we're only talking about signaling from Bob to Alice. So if I promise you there's no signaling in this direction, how would you build a classical randomness model for this? Okay. Well, so here's how it would work. And I think this is somewhat helpful because well, we'll see later on why I'm dwelling on this. But first of all, the non-signaling implies this condition, right? So the non-signaling says that if I marginalize over Bob, then it's a constant for Alice. Right. So this is because she has no input, that means that this output distribution on A is independent of Y. Right. So now when I write down the joint probability distribution, it factorizes like this. Yeah. Sorry, it factorizes like this, right? So this is just writing down the conditional probability form of this. And now because A is independent of Y, I have this decomposition. Okay, and this is great because now from just this simple observation, now we can construct a model and it goes something like this. So Alice's input now becomes, or sorry, her output then becomes the shared randomness between her and Bob. So you just have this common source of randomness here, A with probability PA, and it's just given to Alice. So she just outputs whatever that shared variable was. And now Bob then, when he receives it, he samples from B according to this conditional distribution, B given AY. Okay, so if you don't follow all the details there, I mean, here's the take-home message. So for 2-party boxes, both of them must accept inputs to generate non-locality. Okay, and I'm emphasizing 2-party here because in the next slide, we're going to move to more parties. All right, but this is just a fact of life, as we see here, that if you want to have some quantum non-locality, in fact, you need to have inputs for both parties. All right, good. So let me pause here and take any questions. Okay, so now we're going to add more boxes to the scenario here. And so we're going to consider, so for example here, four parties. And now we're interested in the joint behavior of these boxes again. So we're input-output correlations. But now what's cool is there are a lot of different questions we can ask, okay? So again, we allow for some sort of side information between them, but there's different types of side information we could consider, right? So for instance, we could imagine a fully classically connected boxes. So here there's some classical variable that's shared to all the boxes. So they have common access to it. You could envision that you have a fully quantum connected network here. Okay, so this is some 4-part entangled state with it being entangled to the different boxes. You could have a scenario where you have multiple independent quantum connections. So here I have 3 different quantum sources, and they're distributing independent quantum states, entangled states. And what's important here is that now really the network configuration is going to come into play. Okay, the network topology, because here, if you just look at the connectivity, I have like this particular connection here. But if I rewired my network, I'd get a different topology, and that would lead to a different set of boxes that I can build, because now I'm distributing according to a different topology. Okay, so you could consider that, or you could then consider kind of a hybrid system where you have some of the links are classical, and then some of them are quantum. Okay. And this is where we're going with quantum networks, is something that looks like this, right? Where we have, say, a couple of the nodes have some entanglement source that's distributed, and then you have some classical correlation that maybe sits over all of it, or maybe between part of it. But we're getting now toward realistic quantum networks. And so now the point I want to emphasize again is that this is really depending on the network structure. So when you're trying to compare classical boxes and quantum boxes, you need to first fix your network topology. All right, say which are the links are quantum and which nodes are connected to one another, and then you can compare the input-output behaviors. And this is a new feature that emerges when you're dealing with quantum networks. Okay, and so then the question is that we're interested in is once you fix your network and you have some behavior, input-output behavior, can you generate the same behavior if you replace the quantum sources with classical ones, right? And if you can't, then that's some sort of a new type of non-locality. It's a network non-locality, right? So if I have some input-output behavior that I can't generate just by replacing my quantum sources with classical ones, then in fact I have what we call as network non-locality. Okay, and a practical motivation again is that this is useful for understanding near-term quantum networks, because in near-term quantum networks, or even current-term quantum networks, laboratories are connected by noisy quantum channels. Okay, and what else do we know is that when we build these things, we'll likely have independent entanglement sources across our network. So we're not going to have some very large entangled state that's being distributed to say 100 nodes in our network. Instead, we will have something that looks like this. Yeah, but there'll be independent sources. So you have like down converted photons at different points on your network, and so then the entangled pairs that are generated are independent. And the other assumption is that you have limited local processing can be performed on these states. So what you're not able to do is say receive some qubits at this point and then store it in quantum memory for an indefinite amount of time, and then wait until another pair comes and then wait for another pair comes, right? So there's some limited processing capabilities we have. And so that's why I think this is a very relevant question right now, because what all these parties are doing is they receive their quantum states and they just perform some measurement when they receive it. Maybe they do some very low depth quantum operation on it, but they convert it into classical information. So they get the readout data as soon as it's come. Okay, so this is it's a practical motivation for studying this problem. All right, I'm going to return now to these boxes without inputs. And what it turns out now in this network model, we can remove all inputs to the boxes. Okay, and it's kind of cool. It goes something like this. So here in the two-party scenario, which we had is that we have, as we saw like in the CHSH, you have inputs X and Y and outputs A and B. But now if we're allowing more than two parties, what we'll do is we'll replace our inputs here as shared variables with two new parties that we're going to introduce. Okay, so we map this now to a network where you have four parties. you still have Alice and Bob, but now you have these new parties you've introduced, X and Y. And what you've done is the inputs in the previous case are now shared variables, shared randomness between the two parties, Alice and X, and the Y's is between Bob and Y. Okay, and so now look, in this scenario, there is no inputs. Okay, you're just generating outputs. And it turns out that if you do this type of mapping, then in fact you get equivalent type of boxes. So more precisely, if this is a classical behavior here, then this will be a classical behavior over here, right? So what I mean is that this distribution can be generated by just shared randomness here, and vice versa. So it's an if and only if statement. Okay, so this is a very useful observation. Because here I just give a simple example of two parties, but in fact this extends to an arbitrary number of parties and an arbitrary number of inputs. And so a take-home message is that in quantum networks, there's really no fundamental distinction between boxes with inputs and those without. Okay, if you're allowing constructions like this, then it suffices just to consider scenarios where you're just generating a probability distribution. So you can phrase the question like this: I have some probability distribution, target distribution, that I want to build on my network. Okay, and again, I fix my topology, so it looks something like this. Can I build this distribution using shared randomness on the different links on my network? Right? Or do I need to have shared entanglement on one of the links? Okay. Okay, so this is kind of a useful perspective, but again, it's equivalent. So you can kind of map back and forth between these. And so for the remainder of the talk, I'm going to talk where we still have inputs, and then I'll come back to the scenario where we don't have inputs. All right. But I want to just emphasize that fundamentally, there's no distinction between these two. Yeah, go ahead. Mm-hmm. Yeah. So that is being replaced with the assumption that these are independent randomness.
Experimenters creating the question from different files. So, but like a more complicated network.
Yeah.
Way to understand the no communication that they're really isolated.
I mean, again, I would come back to the independence of your sources. So if you can indeed ensure that these are independently these variables are independent, then you have sort of captured that non-signaling.
Okay, yeah.
Oh, sorry. Okay, so that's on the input side, but then I guess you're concerned about like the signaling between here.
I'm just concerned that if you're looking at really more complicated graphs, I see them online.
Yeah.
Maybe a little.
Yeah. So in this case, you don't have signaling from here because there's no connection between Alice. The only connection from Alice and Bob is coming through this quantum state here.
Can I just ask
Yeah.
a very, very superficial question?
Yeah.
You know, I think when we learned Bell's inequality, it's all about here's a probability distribution. Doesn't have to come from the quantum state.
Yeah.
You rephrased it as an input-output problem. I think I'm okay with that.
Okay.
I guess what I don't understand is that what distinguish, what is the network like? Why do I have to invoke the quantum network? Because once you say that Bell's inequality is the input-output problem,
Yeah.
I thought that the network is a way to push information through, and somehow I don't work in quantum networks.
Yeah,
So
okay.
I don't understand what quantum network.
All right. Let me go back to this motivation. So I'll give you a very practical defense of this.
Sorry, I might-
So the defense would be this, right? So say I build this network, all right. So say here in New York City, you guys build this metropolitan quantum network with different nodes, and you have entanglement being distributed between the nodes. Okay. You turn on your machines and you start gathering data. Okay. How do you know that you've actually distributed entanglement between, I don't know, we're here in the Empire State Building, right? This would give you one way to address that question, because I can compare the statistics I get from just like classical randomness that's connecting them with statistics that require entanglement to generate. So it provides a way to actually certify that you have created these quantum links that you're after.
And the reason we want quantum links is because of better bandwidth, or because of security, or why do people care about quantum networks?
Oh, boy. I mean, I can open this up to the floor. Distributed, you can distribute it. Okay. Well, if you believe that there is any value in quantum computing, okay, that there's any reason to invest in this, then I think you can extend that argument to quantum networks because, well, you have distributed computing, for instance, is one thing you could do where you have some quantum process you want to perform, but you have distributed clients that are accessing this in the same way we do cloud computing right now, right? So now if you have a quantum computer and you want to do cloud quantum computing, then you're going to need a network to do that. Okay. Yep. Okay. All right, good. Okay, so let's look at some specific examples here. All right, and I see I only have 10 minutes left. So the simplest type of network here is what's known as the buy local network, and it just consists of 3 parties, and the middle party then is receiving 2 entangled states, right? So it looks like this, and this is called buy local network. And if you consider the classical sets here, these edges would just be shared randomness that's distributed. And you can write down what it would look like mathematically, right? So you have some independent randomness here, a source here, and then another source there. Okay, and so then if you just see how this works, Bob has access to both variables and his input. So this is what he's generating his output according to this distribution. Okay, and so the question is now, if I have some input output behavior, can I model it in this way, right? And you can see this is very complicated, right? Because now I have 2 variables, and it seems this question seems very challenging, and indeed it is. And in particular, the set of classical boxes is non-convex, right? So previously we drew down this nice picture of a polytope. We could draw these hyperplane separations, and it was very cute. Here it's not cute. And what I mean by non-convex is that I could have 2 boxes, both of which satisfy this model here. So they indeed admits a bilocal decomposition. But now if I take a mixture of them, so now I have a coin mu that I flip, right? And now I'm no longer able to describe the whole thing in this form. And the reason is because what this mu would represent would be some sort of global randomness that's connecting all of these, right? Some correlation that's distributed to these. And so basically it's saying whether or not you play P1 or P2. But in our model here, we don't have this randomness that's shared to all the boxes, okay? So we don't have the convexity. So you can't use the hyperplane separation theorems. You can still deal with Bell inequalities, but now what you need are what's known as nonlinear Bell inequalities, okay? Because our structure is no longer a polytope. Okay, so I'm going to give you one example of a non-linear Bell inequality. Okay, and again, it's simplest case of 2 inputs and 2 outputs. So now, like we did before, we can define correlators. We can define a 3-body correlator, which is just the generalization of this. So this is giving the parity of all the outputs for any inputs. And okay, you can define then an expectation, which is just a linear combination of these correlators. So I define these I and j quantities. And so why are these? What's the intuition here? Well, the intuition is that if I have a bilocal network here, which the classical randomness, then I can in fact factor this product out into a product of two local correlations, two local correlators between A and C. So I get this nice factorization here, and then it's just a simple consequence of arithmetic geometric means inequality that you get this famous what's known as the bilocal inequality. Okay, so you get something that looks like this, and so okay, here's the take-home message. As first of all, you see that this is nonlinear because I'm taking square roots of these correlators. For CHSH, we were just taking linear combinations of the correlators. Now I have these square root terms here. Okay, so that's the nonlinearity. And what it's saying is that if you, in the laboratory, if you generate some input-output correlations that don't satisfy this, then you're failed to have a classical model that can reproduce it. Okay, so one of 2 things must happen. One is that one of these sources is quantum. Okay, that's possibility 1. Or another possibility is that it could be classical, but it doesn't have this network structure. there is some other variable, some other side information that's being fed into these boxes. Okay, so now you're not able to fully certify quantumness in your network, but you're just able to certify that either you have quantumness or you have a different network topology than you thought of, or there's some side information that you haven't eliminated. Okay, so this can be useful for actually trying to identify whether there is side information feeding into these boxes. Okay, so this is what's known as the buy local inequality. And this is particularly useful for entanglement swapping experiments, right? If you saw that the network structure looks something like this, where in entanglement swapping, you have Alice and Charlie who are distributed, initially they're unentangled, but you have some entanglement that's distributed to them. And then in the middle, you do a Bell state analyzer here. Okay, so what a Bell state analyzer is, it's not a full Bell measurement, but you are rather projecting into one of the two Bell states or the completion element there. So it's, or their orthogonal complement. Okay. And you can use the bilocal inequality actually to study this. You have to tweak it a little bit because now there's no input on Bob's side. So you just have this, you're just doing a Bell state measurement here, but you get the same type of inequality. All right. And so then this is useful, in fact, for certifying whether or not your entanglement or your Bell state analyzer is generating quantum correlations. Okay. You can just apply this non-bilocal inequality. And if you repeat this many times, right, you connect these up, this should look familiar to you guys. This is just a repeater chain. So here you have multiple links on this repeater chain, and you're just doing Bell state analyzers. And for each of these, you get an output, right? So, I mean, I view this now, this experiment as just a fancy way of generating input outputs. Your inputs are still on Alice and Charlie's side, but now you have inputs from their boxes, but you also have outputs from each of the Bell state measurements. And so then you can talk about this very large box, and you can ask whether or not you can simulate that with classical randomness on these links or not. Okay. And the inequality that you can use here is this bilocal inequality. All right. Okay. Good. I guess I'm 2 minutes. I'm running out of time. Let me just say maybe one more plug for why this is interesting. Actually, Ellie, are you going to talk about triangle network in yours?
As it shows up in the
As it shows up in definition?
We started a bit late.
Okay, let me, okay, good. Okay, I'll take, okay, then I'll go a little bit longer. Yeah. Cool. So one motivation for this, again, is practical, but it turns out that when you switch to this network non-locality setting, you actually get a greater robustness than you do in the standard CHSH setting. And so let me kind of just sketch out what I mean by robustness. So first of all, in any quantum network, you're going to have noise, right? So I write these as quantum channels here. But so I have my source here of entanglement, I'm distributing it to the two laboratories, but they're going to go through some noisy process, right? And most likely this noise will be uncorrelated. So what I mean is that you basically have one noise channel here and you have another noise channel here. But you could have some correlated noise, which would be something like this. So that means that the noise process on both the arms is somehow correlated. All right. So this is some type of exotic noise. And in quantum computation, actually, this is a huge source of problems, as this correlated noise. In networks, not so much. You can usually model it uncorrelated. But nevertheless, you can still ask if either of these types of noises are on your network, how does that affect your ability to detect the entanglements? Right. And again, violating Bell inequalities is a way to certify entanglement. So the question then is how do the different type of inequalities fare in different noisy environments? Right. And so this was a project that one of my students and I worked on a little bit. And okay, so the take-home message here, in fact, is that if you use these bilocal inequalities, they actually can detect entanglement better in noisier environments. So the main thing is this green square here. This is using CHSH inequality, and you see here's the classical bound. Okay, and you see it drops, and here's the noise parameter. So things are getting noisier this way, right? And you see it drops off. It crosses the classical bound much earlier than if you were to use one of the other network non-local tests. So I make a plug here because there's a reason to go beyond CHSH to actually study these network inequalities. And one of them is, again, it gives you a greater robustness in actually certifying the quantumness. So this was done for depolarizing noise. We have similar results for dephasing noise, and we have amplitude damping. So you can analyze these, and the story is consistent that if you have uncorrelated noise, you get some advantage using one of these bilocal inequalities. If it's correlated noise, there doesn't seem to be much of a payoff. Okay, good. Let me segue to the last part of the talk. And here I'm going to go a little bit fast just to try to keep us on schedule. And this is on the question of generating different types of network non-locality. Okay. Okay, so first is this question of genuine versus non-genuine network non-locality. Good. So I will just give you my 2 cents on it. First is that, curiously, the bilocal inequality is not strong enough to capture all the subtleties of network non-locality. Okay, so what I mean by that is you could consider a network like this, all right, where it looks similar. You have Alice, Bob, and Charlie in a line here, but now look what Bob's doing. Bob's basically saying, what I'll do is I'll break up my processing into 2 parts. I'll do something with Alice, and then I'll do something with Charlie, and then I'll just do some classical processing on my outcomes. So he's kind of playing these games independently with Alice and Charlie. And in particular, you could imagine he does an optimal CHSH measurement between each of these, right? Well, it turns out that in that case, in this scenario, you're able to violate this inequality by the maximal amount, by playing these independent CHSH games. So it begs the question, is this really good? This inequality that I promoted, is this really good at detecting what would be known as genuine quantum network non-locality? Because it doesn't seem like there's something like not genuine here. And really the way that I think of it is that all you're doing is you have independent Bell tests between Bob Alice and Bob Charlie independently. And then you're somehow classically stitching them together, right? You're doing this classical processing here. So you're not harnessing the full quantum network structure here. Bob is not doing anything quantum between both his Alice part and his Charlie part. He's just kind of keeping them separate and then classical post-processing. Okay. And so then this suggests that, in fact, there may be different forms of network non-locality. Okay. And it could come down to exactly what's being done at the different nodes, right? Are you really entangling across the different sources, or is it merely just classical processing that's taking place? And so I think this is kind of a very active area of research, is trying to understand different forms of network non-locality based on exploring the different type of local operations that are being performed at each node. So here's one definition, and I bet you will see this again in the next talk, is that a box exhibits genuine network non-locality if it cannot be generated by independent bipartite entanglements and local classical wiring. Okay, so what it means is that I'm not able to take my network like this and break it up into this form here, where again, Bob is just doing independent measurements between Alice and the Charlie entanglement, and then just doing some classical processing. And this local wiring here, all that means is local classical wiring. So when you see the double arrows there, that means that there's just classical information flowing between his 2 experiments with Alice and Charlie, respectively. Okay, so this was proposed in this recent paper. And so what it means is that Bob must perform some non-local measurements on his 2 systems. Okay, that's like a necessary ingredient for this genuine type of network non-locality. Okay, and indeed, there are examples of this where you can, well, okay, so there is, if you buy this definition, there are examples of boxes you can create that you're not able to generate just by this local wiring. But what is interesting is that, in fact, even though you're not able to generate by local wiring, if you switch your network a little bit, so if you switch your network where, again, you allow this classical shared correlation between all of them, then in fact, you are able to simulate it. So again, it comes back to this key point that emerges when you're studying non-locality on networks, is that your topology really matters when you're comparing boxes. So I have some very complicated box here that I'm creating using entangled measurement here by Bob. And if I just compare to a classical network of the same topology, then I'm not able to reproduce the box. But if I switch my network topology to just fully classical correlation between all of them, then I can reproduce it. Okay. And I guess that's maybe kind of one, again, this take-home message for you guys is that it's really sensitive to the topology of your network when you're making these comparisons between classical and quantum boxes. Okay, triangle network. All right, so this is another example you can consider where it's cool now because now it's not just a line between Alice, Bob, Charlie, but now you give some entanglement between Alice and Charlie. Okay, and so this has been studied, and I'm not, just to keep us on time, I'm going to skip through some of these results here. All right, and I want to just get to our concluding slides here. All right, so some future work in open question. All right, so the first is, how to decide whether a multi-party behavior is genuine network non-local, and according to this definition I gave, right? Can you model it in this particular way, or do you need some sort of non-local processing done on Bob's node? Another question is, what are the different types of network non-locality, and how can they be characterized and quantified, right? And I believe our next talk will speak to this question. Another kind of maybe more technical question is, what's the smallest sized network or box that you need in order to generate this genuine non-locality? So for instance, I quickly threw up this triangle network, but the triangle network example that's used, there's actually 4 outputs for each party, Alice, Bob, and Charlie. But one question that remains open is if I demand that they each output a single bit, can I realize non-locality in this, like the simplest setting? So this is more of a technical complexity question of how complex does my local measurement need to be before I can actually realize this network non-locality. Another direction you could take this is higher dimensional in quantum networks. Okay, this has not really been looked at all. So it's usually just EPR pairs that are distributed on the edges. But if I allow for higher dimensional states, is there a new type of phenomenon that we can realize? Is there a connection between magic state, quantum computation, and network non-locality? Okay, and I put this question more in the slide I skipped over. And let me just give you the reference if you're interested in it. So you can map this triangle network in terms of a quantum circuit, which basically looks like this. So these gates here are creating the state, and then these gates here are performing the measurements. And it turns out that there's a nice relationship that you need to have some Clifford element in your circuit if you want to generate non-locality. And you can see that reference where we map that out. And so I'm interested in this particular question because it shows this connection between computational resources and non-locality resources. And so we're considering now whether this connection can be pushed in terms of what's known as magic states, which are resources for universal quantum computation. All right, and then more generally, what are like relationships between non-locality and entanglement in quantum networks, which we didn't really talk about entanglement at all, besides just the EPR pairs. So there's much more that can be studied and asked in that direction. Okay, good. I guess like 8 minutes over, but I guess we started late. Are there any questions? Yeah. Okay, so pass this around. Is that right? Yeah.
Okay, questions? Okay. Okay, it does work. I mean, I've got one.
Yeah.
In the scenario you showed with the sort of entanglement swapping with all the links.
Yeah.
Well, actually, let me rephrase it first. In the bilocal network, so you commented you can tell the difference between, we'll say, whether one of the sources is quantum or whether everything's classical.
Yeah.
Is there a difference between one classical source and both quantum sources? Is that also distinguishable?
If you just replace like one of these with classical.
Yeah.
Yeah. So I think actually, if you allow one of them to be classical, then I think you can reproduce the box. I think I'm pretty sure this was shown. So in fact, you're testing whether right. So they both need to be quantum in order to generate something that's not classical.
Okay.
Yeah.
And then if you had a chain, if at one point in the chain, one of them.
I don't know. That's a pretty good question.
Okay.
And I think another question would then be kind of like the robustness. So maybe
Yeah.
you have or some loss.
Mm-hmm.
That would be another really practically important question to consider.
Mm-hmm.
Yeah.
Okay.
That's good.
Any other questions? Okay, well, I guess if not, let's thank the speaker again. That was Very interesting.
Thanks, Mark.
Oh, wait, we have one. We have one. Okay. Yeah. Okay. Okay. A little.
Optimal for entanglement swapping.
Mhm.
Yes. Could there be POVMs which do better? No, it will be optimal for entanglement swapping.
Mhm.
You just think of that as just being like a fancy type of teleportation for mixed state inputs. No, the bell state will always give you a bell measurement will always give you the best way of doing it.
Okay. That question was coming from India, by the way.
Okay. There's more that could be said there, but I think it's good. We'll
Okay.
just leave it at that.
Okay. Okay. Mhm.
Oh, it's because I'm still connected. That's why. Hold on. Stop sharing. Okay, there it is. There's a power adapter here that I used if you need that. All right. You tell me I'm all wrong in the definitions.
No, it's good. Those are different from the ones
Yeah.
that I'm gonna advocate for, but definitely I have seen those.
Yeah, because but we don't have the sandbox officer here. Yeah, but I think happening to me that I would wrap it a whole lot. I think
The zoomer in.
and like one actual, like we have cat, then you can try.
Okay, so we see the screen, yes? No, okay.
Yeah, I mean, it might just be just good.
Most everybody.
Yep.
Sort of ran to get coffee.
Nice, that's working well. Okay.
Yeah. There's no time pressure here. So.
Okay.
And I now, the next 3 months.
Let me see how people are doing. Well, then you're bringing. I guess well, so the reason at least I like. You don't have.
And they. From that, they hold ready, they grab.
And so if I.
Kind of. Based on my.
I always reset my. Still, and I have.
Just to make it look good.
Exactly.
Yeah.
Oh, okay, you don't. Reset, yeah, I mean, the first.
Yes.
Oh, yeah, that's
What about Mike?
That part has been that you and the people who
then,
official property promotion, they tend to think it's more complicated.
Okay, let's go ahead and get started. The next talk is given by Ellie Wolf from the Perimeter Institute up in Waterloo. And it's another talk on network non-locality, which as you might surmise is now a pretty hot topic.
Thank you, Mark. I really appreciate the invitation, and I really appreciate Eric going before me because he introduced a lot of the subtleties having to do with non-locality, which will make this, I think, much easier to understand. So I'm grateful to him, even though we didn't really coordinate that much. So I am not going to be talking about generic networks and look what you can do in this network and look what you can do in the other network. But I wanted to say, even if we were not on a network, if we were in a situation where you just had one giant quantum system, how would you prove that what you've got is not a bunch of small systems? So this is kind of just trying to get the definitions right. I was explaining to my brother-in-law, let's see if I can get this working, what I was going to talk about today last night. And I was explaining that what I wanted to do is to encourage people not to choose a definition after the fact. And I really don't think that as a field this has been done, but one might imagine that you do something in the lab and you say, okay, what is our thing good for? So you have some technology and then you invent a benchmark and you say, look, this can do that. It couldn't be done before. Therefore, this is great. But a little bit that's drawing the target after you've shot the arrow. What we'd really like to do is to say, before we imagine what other technologies are available, let's set the right thing to strive for. Let's all sort of agree on appropriate benchmarks and thresholds and accomplishments, and then we can aim for those. Maybe we can achieve them, maybe we can't, but we can decide what is worth pursuing as opposed to what's expedient. And I'm coming from Canada, so I wanted to just show a slide or two about the Perimeter Institute in case you thought that Canada was all sort of rural villages and people with accents. The Perimeter Institute is in Waterloo, which is one of the smaller cities in Canada, but it's a lovely institute. We've got about 200 people typically in the building. It's worth swinging by. There's a lot of stuff going on. It is an institute for theoretical physics only. So the only sort of equipment which is used by the physicist is a coffee machine, but it's really good. I will also, again, I'm glad to be here. I do have, something I want to proselytize, but there is a group that I'm not personally affiliated with, which is the Perimeter Institute Quantum Intelligence Lab. And based on what I was hearing about from Sandbox and from Connect, it feels like you should probably connect with these people because this is like a spin-off, which is half affiliated with Perimeter. A lot of sort of Perimeter researchers also are associated with this. It's in the building next door to Perimeter, but here they focus on quantum and AI and that interdisciplinary intersection and optimization, sensing and networks. Whereas I'm coming at it much more on a sort of foundational basic science side and trying to just understand what quantum theory is telling us and not trying to do anything in particular with it. So the topic that we need to cover is both entanglement and non-locality. These are different things. Entanglement is a property of a theory. You can't go and see entanglement. You can't measure entanglement. You can measure consequences of entanglement. Non-locality is the kind of operational predictions. So we often talk about like the way we model a theory and what the theory predicts. And these are two different sort of features of quantum theory, which are non-classical and surprising and have had lots written about them. So let's just start, before we consider this case of a system of multiple particles or multiple photons or multiple parties, let's just consider the bipartite case. So partite is just the adjective form of a party. So bipartite means we're dealing with two systems. So you can think about this as two photons. You can think about this as two NV centers. And we want to understand at the level of quantum theory, what does it mean for something to be entangled? And entanglement is defined often in terms of the thing that you can't create if you are only availing yourself of classical resources. So entanglement is the thing that you get when you employ non-classical resources to get there. In the sense that if you could have a quantum channel, if you could create like an entanglement thing, but there's a lot of things which can't create entanglement, right? If you have these two systems, which let's say there's no entanglement to begin with, and you do stuff to one, and then independently somebody else does something to the other system, you're not going to create entanglement. In fact, if you do a coordinated action on the two systems, but the coordination is entirely done by means of shared randomness, like this bit string, you're not going to create entanglement. That's local operations with shared randomness. And in fact, even if you do sort of a coordination where you've got these two labs, let's say Alice's lab and Bob's lab, and they both have their systems, and they want to now create entanglement between the two labs. If they get on the phone and call each other and send email instructions, like, okay, now you do this and I do that, they still can't create entanglement between them, even though they're availing themselves of classical communication. And there is a larger set of operations, which is defined kind of in the mathematical abstract, which are separable operations. And it's simply defined as the set of all things that you could do which wouldn't create entanglement. Well, obviously it can't create entanglement because it's the definition. So what example is an entangled state? Well, it's not that. If you have a pure state over two systems, A and B, and it factorizes so that you can express it as a state on A tensor a state on B, that is a product state, which is not an entangled state. But of course, just because I have a state that doesn't factorize doesn't mean my state is entangled. That's only for pure states. For a pure state, it's not entangled if it factorizes. Full stop. For a mixed state, we would say, well, a mixed state is a convex combination of pure states. And so if we can get there by taking a mixture of product states, then it's not entangled. Right? So it has to be that whatever our state is, we can't get there by mixing product states. These are all like definitions where I'm not telling you what it is, I'm telling you what it's not. We're going to come back to that. So we can now talk about non-locality, which is the operational predictions of quantum theory. As Eric pointed out in his talk, we have a notion of a local model, which is when we have this side channel, which is the shared randomness, as opposed to a side channel, which is qubits, correlating these two things. And we get a conditional probability distribution, which I'm going to write as P of AB given XY, A and B are the outcomes, X and Y are the inputs. And so you get this distribution with two outputs for every time you pick two inputs. It's a family of distributions in X by XY. And if it can be expressed as some summing over a variable, let's say lambda, where you've got these response functions, A depends on X and lambda, independently of B depending on Y and lambda, then that's a local model. So the things which are non-local, one word, non-local, are the things which don't fit that form, which is awkward. Like, how do I know whether this particular correlation is or is not something that is of this form? Because it's this quantifier lambda, which we don't actually observe, but that's the value of Bell inequalities, because Bell inequalities allow us to sort of say, oh yeah, this is clearly not of that form because everything of that form satisfies a Bell inequality and our thing doesn't. All right, what is the going on here? So both entanglement and non-locality are defined apophatically. This is a word that I encountered in terms of describing like what are Quitrit states. I love this word. It basically means I define something by telling you what it is not. It comes from, I guess, theology studies where people talk about like describing the divine by what it is not, but it's, you can just use it for anything. And there is a connection between entanglement and non-locality. Not only are they both apophatic definitions, which is if you're not this, then you're entangled. If you're not this, then you're non-local. But one is a witness of the other. So if you have these two people, Alice and Bob, and they generate a correlation, and it's non-local, then you know that the side channel information was not a separable form of side channel information, but was entangled. So we call it a device-independent witness of entanglement. What's device-independent as a paradigm? I think about this as not being duped by a sleazy salesman. So if somebody says to you, oh, it's very good, much entanglement, so useful, you could be like, a little bit skeptical. Go prove it to me. So I imagine that like you're on like a convention floor at say an APS meeting, and all these people are selling these devices, this chisels, this, and somebody says, look, this is the thing which produces entanglement. And it's like fancy, but how do you know? So what you can do is you can say, without opening it up, you perform this task, you see whether the device can pull it off. If it can, then you know that it's authentic, right? So the device independent paradigm is where you don't open it up, but you see that your resource is capable of doing something. And in order for it to be capable of doing something, then it tells you something about what's inside. So this also goes back to, I think, and what you were talking about in terms of rigidity, where we also refer to that as self-testing. We've seen a few people who've said what exactly is Bell non-locality. So one form of it, it can be done in different systems, but in photonics, we might imagine that there are entangled photons which are generated, say by pumping a nonlinear crystal, they go off, and then they get measured. But we need to have now settings and outcomes. So what the outcomes could be, does a sensor detect the photon? Yes or no, right? Do we get a click in a meter? And so we have one for Alice, one for Bob. This gives me 0 or 1 outcomes for both of them. But then what's a setting if we just have these light detectors? Well, we could insert polarizing filters and we could put them horizontally or diagonally, and those would count as the 2 settings. And if we do this, we generate statistics, which are described at the sort of theoretical level as there is a state, there are projectors associated with what Alice is doing and what Bob is doing. Those projectors live in different Hilbert spaces, assuming everything's discrete, and you buy the tensor product paradigm of quantum theory, and you could get these kind of correlations. And they give us statistics such as these. These are an example of a data table. So you'll note here that this is A and B, X and Y are all taking 2 values. I'm indexing them by 0 or 1. And you can read this data table here. It's not working. Oh, it is working? It is working. Yes. So in this particular corner, we're looking at X is always 0 and Y is always 0. So this is when Alice is doing her 0 setting and when Bob is doing his 0 setting. And then you get these 4 probabilities, which are associated with the 0, 0, 0, 1, 1, 0, and 1, 1 outcomes. And of course, all those 4 probabilities should add up to 1. So if you check, those 4 probabilities in each sort of matrix block add up to 1. And what you see here is, in this situation, we talk about correlation, which is that the vast majority of the events, the weight of the probability, 80% of the time, has Alice's outcome being the same as Bob's outcome. And that's true if we go to this paradigm as well, where now Alice is doing a different setting, but Bob is still doing the same as the original setting. It still is the case that Alice and Bob typically will get the same thing, which means if it goes through Alice's polarizing filter, the photon, then the photon will also go through the polarizing filter on Bob's end and vice versa. And if now Alice switches or Bob switches and Alice stays the same, they still mostly have correlation. But in the last case, they have this anti-correlation. And that gives us these kind of statistics, which is summarized over here. And these are signatures of non-classicality. So if you see this kind of stuff, you're going to violate a Bell inequality. And this extremely non-signaling box that Eric made reference to, you just replace the almost always with always. So quantum theory actually can't pull that off. But one could imagine a stronger than quantum theory where you replace these statistics with almost always. And instead of being 0.4, you raise it to 0.5. And instead of having 0.1 on the sides, you just have 0. So what is going on is we've long appreciated now that entanglement is a property in quantum theory where we can describe these very pure objects, which are vectors in a multi-partite space. And the description of that is indescribable in terms of the parts. So Anne, I think, mentioned this in terms of like the slices of the apple don't give you the whole apple. The early physicists who were encountering this, Einstein among them, thought that that was uncomfortable. I think rightly so. How bad exactly is it? Maybe it was a little exaggerated. But in 1964, John Bell realized that entanglement is not just an artifact of quantum theory, but is inherent to quantum theory, which is to say any other theory that would make the same operational predictions as quantum theory is going to have some notion where you're going to have information which is distributed beyond one place. Of course, just because that was noticed in 1964, that any theory which would agree with quantum theory is going to be stuck with this, doesn't mean that, in fact, quantum theory is the correct theory of the world. So how do we know that we live in a world where entanglement's a real thing? And so loophole-free Bell experiments were eventually conducted in 1981. And then, well, I would say Bell experiments were conducted in 1981. Then later on, we have these loophole-free Bell experiments, which really sort of do everything at space-like separation, simultaneous. And eventually we get last year's Nobel Prize, which is very nice. It's a good time to be talking about this because we recognize the significance that Bell's theorem has had in terms of how we understand reality, how we understand quantum theory. All right, this is all about bipartite entanglement, bipartite non-locality thus far. What changes when things go multipartite? We'd like to have a notion of, is there something new if we have three parties? So let's talk about historical convention. It's a little bit hard for me to find the correct citation for this. I would think it's maybe Sievink, but what constitutes a sort of entangled state, which has three systems in it, and we would say is something genuinely new, goes beyond all forms of entanglement that we've ever seen before. And so one idea is, well, you know what would be not really new is if we just had entanglement between two of the parties. Okay, yeah, that's clearly going to be not new. And so if we have a pure state, ABC, and it would be equal to some entangled state for Alice and Bob, tensor some completely different state for Charlie, we would say, yeah, it's entangled, but it's not genuinely three-way entangled. It's just two-way entangled, and you've stuck something on. And so in order to be genuinely three-way entangled, you can't be entangled across any one of the ways of grouping two of the three parties together with the other one not. So if basically you have a pure state and you confirm that this equality does not hold, and this equality does not hold, and this equality does not hold, okay, now it's entangled. Now it's genuinely three-way entangled as opposed to entangled. And if we wanted to sort of extend this definition for mixed states, which is typically what we have, then we would say, okay, what we mean is that now we can take mixtures of the sort of things which are 2 versus 1. So this is like these 2 versus 1, those 2 versus 1, those 2 versus 1. And if we take some convex combination and we get a mixed state, we can give a formal definition as well. Then we would say this is not genuinely three-way entangled. So we're still keeping this apophatic approach where we're saying it's genuinely three-way if it's not that. All right. And so this is just another giant slide of a formula if you really wanted a equation to describe what is genuine tripartite entanglement using this historical definition, which I actually am not going to endorse ultimately, but this was the first thing that was put out. Okay, and now let's do the same thing for multipartite non-locality. What would make sense as a notion of genuinely something which is a non-local phenomena involving three parties or three systems, which is not anything we've ever seen before? So we would say, right, it's sort of, we're going to follow the same idea, which is we have a notion of things which are not classically explainable for two parties. And so then we're going to say, let's take all of the things which are not classically explainable for two parties, tensor some independent probability distribution for a third party, all the different ways of doing that, convex mix, and then if it's not that, then it's genuinely three-way non-local. So here what we're saying is we're mixing over these probability distributions, which are sort of two parties having their own thing going on, tensor something else, where the two parties have something going on is the outermost set that Eric talks about. It's just any legitimate probability distribution, including signaling ones. We're not referring only to non-signaling ones. But if it can't be expressed this way, it's genuinely tripartite entanglement. So this was definitely, I can give you the correct citation for this one. This is due to Svetlichny. And now, well, I would just say one thing that is definitely good about these two definitions, which is fair, is that we still have this kind of device-independent relationship. Namely, if you observe a non-local correlation, which is genuinely three-way in the sense that it can't be expressed like so, then you know that whatever state was used to generate that would be a state which is genuinely tripartite entangled, using the definition of genuine three-way entanglement that we proposed. So it's at least they're consistent, right? Like one is a witness of the other. All right. How do we think about entanglement being genuinely sort of full way, or like if we observed, let's say, a distribution with 4, 5, 6 parties, we would say, oh, this distribution or this state over 5, 6 parties is actually three-way entanglement only, or this distribution over 5 parties is only 4-way non-local. And so there's different ways that you could count this up. I don't think it's that complicated, but one is by counting basically the size of the largest group. And you'd say if in any way that I convex decompose this thing, I need to have a group of this size, then that's the measure of non-locality. So if you can get away with groups of size 2, it's only 2-way. If you need a group of size 3, then it's at least 3-way, and so on and so forth. And the other way is saying like, well, how many ways can I split it up? Because if we're dealing with something which is not entangled at all, and you have 3 parties, then you can partition it into Alice, Tensor Bob, Tensor Charlie. If you can get only one partition in, like 2 versus 1, then it's maybe 2-way, but not 3. So now we could go to 4 parties, and we could say, well, if we can describe it as a 3 versus 1 or a 2 versus 2, that's still very, very close to maximally entangled. But if I can do like a 2 versus 1 versus 1, that's a lot better or cheaper, we would say, than a 2 versus 2, because it's a higher partition. Okay, so these definitions, including non-locality and entanglement. Yeah. Yeah.
Do I have to think of density next week, or does this all equally apply to pure states?
It equally applies to pure states, and it's much, much easier to think about this for pure states. I provided definitions for density matrices because typically that's what people ask for, but it's much easier to describe it in terms of pure states. So yeah, think about it as pure states.
Right. So then I'm gonna ask a question.
Yeah.
That's something where so it seems like there are 2 separate sort of aspects of this question. One of them is the structure of multi-part entanglement, and the other one is the amount. You can have very weakly entangled states that are non-classical, but the yes or no question is you insist on they will be entangled. But
Yes.
But they're.
Yep.
Right. Okay, so if I think of multi-partite kind of a setting and just asking like, what are my cartoon like sort of things? So there are 2 things that I know of that can be used, GHD state or any other kind of like a cat-like sort of a state that has a very flat structure of entanglement, but not so much like one bit kind of thing. And so the question is this so yeah, I guess my other question was going to be that like if I really want to define a general tool for dealing with multi-part entanglement, and if I wanted to generalize Schmidt spectrum from bipartite, there's the higher order singular value composition. This is sort of related to that. What you're sort of describing it in kind of more kind of population sort of notion. I'm trying to relate it to the pure state sort of idea.
Yes. So
and like I said,
so no, let's do it. So we would, I think all of the definitions would agree that a GHZ state for 3 parties is genuinely three-way entangled. So like I'm gonna propose a few different things here, but we all agree with that. And the notion of does it factorize, right? Like as A, B versus C, we can think about like as a bell pair tensor, let's say just the qubit in the 0 state. Or we can think about like 2 bell pairs, one for Alice Bob and another one for Charlie and David. That's a 4-partite state, but it partitions. And the way I would express this in terms of singular values is that if you take your state and any singular value decomposition is relative to a particular partition, right? So you can say like, I want to consider the singular values of Alice versus everybody else, or of Alice Bob versus everybody else. And we would say for a pure state, it's genuinely multi-part entangled. If every single time you do a Schmidt decomposition, any way you partition it, it has a Schmidt rank which is not 1, greater than 1, right? But if there's any partition where the Schmidt rank is 1, then we would say, it's not genuinely multi-part entangled. Yeah. Yes.
So, first one, I understand that's the definition of the definition of three-partite or entanglement.
Mhm.
But now for the other one, if I want to say that it's a, if we're three-partite entanglement, do I do like the number of particles minus the number minus this minimum partition count?
That is exactly what you do. It is the number of parties minus the number of partitions. And that is the degree of entanglement.
And it's the same, I guess.
No, it's not the same. So we can construct, for example, let's say 2 versus 2. It's only one partition. So for 4 parties, it's 4 minus 1, which would be like, it would be considered level 3, not quite level 4, but level 3, because it's one partition, but 4 parties. But if we measure it by group size, it would only be level 2. Whereas if we consider 2 versus 1, that would be level 2 according to both. Yeah, I don't deal with either, but I've seen them. So I didn't want to sort of just in a survey say that there was only one way of thinking about it. But it's a good question. All right. So since I'm about to launch into a criticism and say like, oh, these definitions which have been historically used and cited, many hundreds of times, we shouldn't use them anymore. I do want to sort of at least say there are some things that make sense here. Namely, just as we define non-locality for 2 parties without any definition involving quantum theory, right? We can just define classical and the things which are not. And so non-locality can be defined without assuming that quantum theory is true. And then it turns out that quantum theory allows us to have non-local correlations. So this is a definition of tripartite non-locality, which again, the definition of non-locality doesn't make any reference to quantum theory. It's just the definition of here's a probability distribution. If you can express it in terms of these other probability distributions, which are again, just general probability distributions, then it's not. So I like that theory agnostic part. I like that it's device independent. And I would say if we are thinking about classical communication, if we're thinking like, what do you need to achieve bipartite entanglement is you need to have a quantum channel open between these 2 sites so that you can do a quantum operation which connects them. Then in a world where you're saying, yeah, it's okay for these 2 parties to have quantum communication, just not all of them, right? Like Alice and Bob can have quantum communication going on, but not Alice with Charlie or Bob with Charlie. Then the kind of distributions that I would allow for Alice and Bob, they don't have to be non-signaling because Alice and Bob are going to be connected by a communication channel, which is the quantum communication channel. Okay, but here are a few problems, and I think that they're big problems. One is this definition of tripartite non-locality, and this is only an issue with the non-locality definition, is it's unstable under wirings. What does that mean? I'm going to explain that in the very next slide. It's also unstable under parallel composition. What does that mean? I'll explain in 2 slides. And then there's this business about if classical communication were free, we would have a problem, and I'll explain that in 3 slides. Okay, so this is what I mean by instability under wiring. If we have a tripartite box, which is X and Y and Z are the settings, A, B, and C are the outcomes. I've put an arrow indicating time. So this is backwards convention relative to Eric. His picture of the boxes had, the outputs on the bottom. I'm having the outputs on the top. Imagine that it was an example of a tripartite box, which is not genuinely 3-way. And in fact, we can express it as a convex combination of Alice Bob stuff and Charlie on the side. So which is stronger than usually, because usually I can say, like, I can express it as a convex combination of more than one way of doing partition. So I'm telling you, this is a box which is so not tripartite that I can actually point to the particular partition, and I can say, using just this one partition, notice that I can express this box by just mixing things which are separated by this partition. So there's some AB given XY going on. There's some, I should say rather, it's some BC given YZ going on, and some AX going on, and then they're just being combined by lambda. So I start with a tripartite distribution, which satisfies the first equation. So it is definitely not tripartite. And then I do something on the partition, which is pulled away from everybody else. right? So we already said it's, Bob and Charlie are sort of living in their own world, doing their non-classical thing, but they're not interacting with Alice. They're only connected to Alice by shared randomness. If we take this box and we construct a bipartite box out of a tripartite box by ignoring one of the outcomes, namely Bob's outcome, and using that outcome as the input for Charlie. This is a reasonable operation because Bob and Charlie are together, they're colluding, they are in communication. So there's no reason why Bob couldn't get the outcome and then email it to Charlie, and then Charlie would be like, all right, I'm going to now put my setting in that position. And then you do this, and ultimately you get these statistics, which are now just AC given XY. It's a way of creating a bipartite box from a tripartite box using what we call a wiring. If you do this, the resulting bipartite box is straight up non-local. And that's weird because we haven't done anything across the Alice versus Bob Charlie partition. We've just done something internally in the Bob Charlie partition. And we started with this thing, which was separable as Alice versus everybody else. And now everybody else did something, and it's no longer separable as Alice versus everybody else. So that tells us something funky is going on. Yeah. Yeah. So if we had space-like separation between all the parties, then I would say, yes, this would be a forbidden operation. But in a paradigm where we're allowing for communication between two of the parties, but one of them no. So you can imagine like Bob and Charlie are sort of in one site, and it's kind of an artificial distinction, then I would say this should be allowed. Well, I would say Alice is still far away. Like, so you can have space-like separation between Alice versus Bob Charlie. Yeah. Yeah.
So you'll produce, I'm not following the equation.
Okay.
But the issue here is the XA channel is now no longer separated from the right. Is that right? By allowing this intercommunication.
Correct. Yes. All right.
Right. So he's not communicating across that.
I know, but I still feel like.
Let's come back to it. So parallel composition is, and this is now a criticism not just of non-locality, but of entanglement itself, which is, suppose that I have three labs. I call it Alice's lab, Bob's lab, and Charlie's lab. Alice's lab can have more than one qubit in it, right? It's a four-dimensional system. So suppose that Alice has two qubits in her lab, one of which is entangled with Bob, the other of which is entangled with Charlie. And also, Bob has two qubits in his lab, one of which is entangled with Alice, right? So on and so forth. And so basically, I've told you that this link over here is this Bell state, EPR pair. If we apply our definition of tripartite entanglement that we've used, so for pure states, we mean if you were to factorize it as Alice versus Bob Charlie, then are there any situations where the Schmidt rank is 1? And the answer would be no. There's no way of doing a factorization of this 6-qubit state where you pull off Alice's 2 qubits and compare them to Bob Charlie's 2 qubits, or you pull off Bob's 2 qubits from the other two in such a way that it looks like there's no entanglement. And so any definition which says, oh, it's just about, can I express the whole thing as a product? It doesn't work. This is going to be considered genuinely tripartite entangled using the definition that we've seen so far. But it's just a bunch of EPR pairs, which I think was Eric was getting to in like the 4th section of his talk, which is, well, it really feels like we're not even stitching together anything. There's just no stitching at all. It's just they're in parallel, and all of a sudden now it's genuinely tripartite. And is it reasonable to say that if I have these 3 pairs of EPR states, then that's the same as something which is genuinely 3-way? And in fact, we don't even need all 3. If we just had 2 EPR states, one between Alice Bob, one between Bob Charlie, it would still be, relative to the previous definition, genuinely tripartite entangled, because there's no way of doing a partition which would create a product. But it's just parallel composition. And of course, the same is true for non-local boxes. This is very much, I think, what Eric was saying very explicitly, which is that you can create this example where you have a non-local box between Alice and Bob, a non-local box between Bob and Charlie, and then you just stick them together in this kind of way so that Bob sends his setting to the two places, gets two outcomes, and then just reports them both. You get a box, which is, according to Svetlichny's notion of multipartite analogicality, a genuinely tripartite correlation. But it feels like it shouldn't be, which means there's an issue with the definitions if you think this should not be considered genuinely tripartite. Yeah.
Take those two out there, three, sort of do stuff that was create something that does work, like something we're not worried about. So then I think, yeah, that's how it should be.
Okay, we're going to get there in 3 slides. I'm so glad you said it. Yes. So, and the third issue is if classical communication were free, and this is a bit of a prelude to that. We're saying, okay, LOCC is fine. It's just the quantum communication which is a problem. Well, you know what you can do with classical communication? You can violate Bell inequality. Because if Alice has a setting, and that setting can be communicated by the phone, not by a quantum channel, to Bob, then Bob can perform an operation which will violate a Bell inequality. So in a world where classical communication is free, then when I violate a Bell inequality, should I conclude that this sort of explanation over here, which is the set of all correlations which are local, this is a causal depiction of the local model. So clearly it's not that. But if classical communication is free, then I should say, like, yeah, this is the correct explanation behind my Bell inequality violation, as opposed to assuming that you're witnessing quantum entanglement. Maybe you're not witnessing entanglement. Maybe you're just witnessing classical communication. Because of course, the Bell experiment, kind of we say, like, what's loophole free is if you do it in space-like separation where the parties can't communicate. So is communication free or is communication not free? You got to pick a lane. So there have been some proposals which have said, let's not use a definition in terms of signaling boxes, but let's try to do a decomposition in terms of non-signaling boxes. So you can still have like Alice, Bob doing something and Charlie doing something off on the side. But whatever Alice and Bob are doing, it should be a non-signaling box as opposed to a general, any kind of valid probability distribution. This fixes a lot of things. It is now stable under wiring, among other things. It's consistent with the idea of communication not being free, just sort of non-classical common causes being free. But it still leaves us with the issue of instability under parallel composition. So it's nice. It's stable under wirings. It is still a device-independent witness of entanglement, which is like a slight revision of Svetlichny's definition, which I've seen. But it's still unstable under parallel composition. And if you were now to go and try to sort of determine whether or not something is tripartite entangled, using such a definition can be expressed as like a convex combination of things at product, that's a really, really hard thing to do. And the reason it's particularly hard is because it's very easy to list all of the deterministic strategies. So if you want to list like, what are all of the valid probability distributions for Alice and Bob, it's easy. If you want to list all of the non-signaling probability distributions for Alice and Bob, because they're going to be a unit here in your decomposition, that's a hard problem because you now need to understand what are the set of non-local boxes, which include indeterministic boxes. So in practice, it's a lot easier to falsify Svetlichny's first definition than these revisions to Svetlichny's definition. And of course, in principle, you could say, like, why are we using non-signaling boxes? You want to create a device-independent witness for entanglement. Let's say that whatever Alice and Bob are doing, it's got to be some quantumly realizable box, which is less than a general no signaling box. But of course, now it's going to be basically impossible to actually solve anything and make any proofs because it's very, very hard to characterize this set of quantum correlations. But okay, this is just about saying, I think it's appropriate to say we have many definitions on the table. If they are all justified in a various sense, maybe it makes sense to sort of say, like, I'm going to pick the definition for which I can get a result, as opposed to stretching beyond where you can reach. This now goes to the question about maybe instability under parallel composition is not a bug, but a feature, which I think is what you were saying. Because in fact, if we do have communication, then from lots of parties sharing APR pairs, you can create pretty much any entangled state you want using classical communication. But it feels strange to say we're going to consider classical communication at the level of states, but no communication when we start now dealing with this world of boxes, because are we imagining that people are in communication, or are they like space-like separated and everything's happening simultaneously? In fact, if you try to say, okay, we're going to allow states to be generated through communication, but we're going to allow the parties to perform a Bell experiment at space-like separation, so where there's no communication, even if we don't go multipartite, we already start seeing a bunch of inconsistencies at the bipartite level. For example, we have a notion of a state which is more versus less entangled, right? It's less entangled. If from a more entangled state, I can get there under LOCC. But we also have examples of distributions in the bipartite case, like Hardy paradox, where you can achieve this non-local task with a partially entangled state, but you cannot pull it off with a maximally entangled state. That's an anomaly. How is there something that I could do with a weakly entangled state, but I can't do it if I have a more entangled state? You just told me that the more entangled states are as good as the less entangled states, because from a more entangled state, I can make a less entangled state. But the less entangled state can do this task, which the more entangled state can't. It's because we're mixing apples and oranges here. It's an inconsistent resource theory. Either communication is free or not. So if you want to evaluate entanglement on states for the purpose of understanding Bell inequality violation, you shouldn't be using LOCC. You should be using LOSR, because that's the paradigm. But this also goes to situations, again, only two parties. There are Bell inequalities, and you can ask, if I add noise to the state, what sort of state should I choose to remain, for which there's a Bell inequality, which will show that it's non-local, and there are going to be some partially entangled states which have more noise robustness than maximally entangled states. There's also issues with like just how do you achieve the maximum violation of a particular Bell inequality? So just a straight up normal Bell inequality with more than two outcomes, and you can get there with a partially entangled state, even though you can't get there with a maximally entangled state. And this is all to say you can't do LOCC for states and LOSR for boxes. You got to pick a lane. But to that point, if you do have classical communication, then this is a situation where you'd have like Alice and Bob sharing an APR, Alice and Charlie sharing an APR pair, and Alice also just having whatever she wants in her own lab, and then she can teleport. And so this gives us a protocol which would give us any kind of state we would want, actually a tripartite state. So I would agree that we have to sort of pick. All right. Since I'm not going to feel rushed for time, I'd say we're maybe 20 minutes out, but I would say, is there any hope? Can we find a definition for multipartite entanglement, multipartite non-locality, where everything's consistent, where we get this kind of device independent witness, where it's theory agnostic, and we don't have problems where we're saying, oh, we're assuming there is communication when we evaluate for states, but there's no communication when we're sort of thinking about boxes. And there is, and it's totally inspired by quantum networks. So that's sort of this new proposal that I want to offer, which is to say, and I think this is going to be intuitive at this point, something is genuinely tripartite entangled if it can't be achieved by local operations on lots of bipartite stuff. That's it. So what we're saying here is, if you have some sort of quantum network, which has these two-way sources of entanglement, so you can think about like pumps and beam splitters, but every party has now two photons coming into the lab. Whatever these parties can produce, if it can be made that way, it's not genuinely tripartite. If it's genuinely tripartite, is if you really need to have somewhere in your network a three-way source. But if your network can achieve this state with two-way sources, then it's a two-way state. That's the definition. So this is like the same sort of causal structure definition, where we talk about systems and variables. But this is, of course, we're not generating a probability distribution here. So green means quantum. So we've got quantum states at the bottom and then quantum states coming out. So this is basically a circuit which produces quantum states. And what kind of circuits are we talking about? It's a circuit where you have these three different ways of preparing entanglement, and then they get processed, combined in various ways. And then the output of the processing are the sort of each party. And so you can generate a bunch of tripartite states. And my proposal is, if your tripartite state can be generated by the circuit, it's not genuinely three-way, it's really two-way. And we could do a very similar thing for, well, let's now talk about tests. So there's definitions and tests. Yeah.
Like this example where three parties, one of them has like a three-particle circle inside it, right, and they spread it to create how does that fit in?
So that required a round of communication, right? So the example of where one of the parties had this three-way thing inside is one where Alice does the measurement, communicates the outcome of her Bell state measurements over a classical channel to Bob and Charlie, and then Bob and Charlie would do unitary corrections based on the outcome of Alice's measurements. No classical communication. So this is a situation, the causal structure is one where there is no arrows connecting any of the parties. It's just going forward. You've got these two-way sources, and then the operations are entirely local. So this is the LOSR paradigm. Lambda is a classical variable, and then these are bipartite sources. All right, how do you test? If I tell you like, okay, here's my quantum state, is it genuinely three entangled? Because it would be like not so nice of me to come up here and say, here is a definition, which I think we should all be using now, without telling you a way of actually checking whether a quantum state satisfies or is out of the set. So this is a quick idea, which is if your state could have come from that circuit, then you could build a different circuit using the same pieces. So if there would have been any procedure of that flavor to build a tripartite quantum state, then you should be able to take the same sources, same local operations, but connect them in this new way. So I've got this kind of Alice Charlie source, but independently prepared up here and down here. And so then there's this party that I'm calling Alice. It's like an Alice because it's connected to an Alice Charlie source and an Alice Bob source, but it's not the only Alice that I'm going to keep around. I also have an Alice down here, which is also connected to the same two states. So this is just a way, it's a thought experiment, if you will. And if I were to recycle the same circuit components to create this now six-partite quantum state, I would start to know certain properties of this six-partite quantum state. I would know, for example, we call this an inflation because it's a causal structure, but we do a thought experiment and imagine recycling the same components to do a new idea. So here, if we look at the marginal state on A1 and B1, that marginal state should be the same as the Alice Bob marginal state in the original circuit before I rewired things. And so we've got a couple of these links. And then we have also notions of separability. So in the original network, if we asked, is Alice entangled with Bob? The answer is yes. But if I now ask here, is Alice entangled with Bob? You need to tell me which Alice and which Bob. Alice is entangled with this Bob, but this Alice is not entangled with this Bob. So I could say like, whatever this state over six parties would be, and I don't know what it is, I just know something about its marginals coming from these links, but I also know something about its separability, which I could say, like, for example, means that it would be positive under partial transpose if we take marginals where they're separate. So if you consider like Alice 1 and Bob 1, Alice 2 and Bob 2, that marginal on four parties, there's no entanglement there. So there should be like positive partial transpose under such condition. And of course, symmetry, because if you change all the ones to twos, it's basically the exact same thing. And now this defines a semi-definite program. Because you could simply say, okay, we started with this 3-qubit state, and I could ask, is there any 6-qubit state with these properties? That is a question that you can just pose to a computer, because you can just fill in a density matrix and say, can this density matrix be filled in such a way that all the eigenvalues of this 6-qubit density matrix are non-negative, subject to these conditions? And you can get a yes/no answer. And if the answer is no, then the original 3-party state that you got is genuinely tripartite entangled. So this is a lot to take in, but it's this idea of using inflating your causal structure to get answers about things that could or could not be achieved in the original causal structure. All right, let's do the same for, well, let's just summarize here. We can always do a semi-definite program, which will allow us to sort of get results. We can also obtain inequalities on states. So if we want to know, like, if your state violates this inequality, then it was generally tripartite entangled. We can do that, and we can consider different forms of inflation with different symmetries, which can be useful. A lot of references here. I'll put them up again at the end. I don't want to do that. Yeah, so I will point out a couple of results. Probably none of these are terribly shocking, but if I give you a graph state on a completely connected graph, it has been proven that it's at least 3-way entangled by this new definition. So any quantum network which only uses 2-way sources, you can't achieve any graph state. Okay, that's nice. What about the GHZ state, which is sort of this paradigm? Like, is the GHZ state for any number of parties always genuinely n-way entangled? Yes. All right. In terms of comparing this definition to the previous definition, we would say hitting the threshold for this new definition of three-way entanglement is just a higher threshold. Because if it is genuinely three-way entangled relative to this definition, meaning it can't be explained like this, then it also can't be expressed as a convex combination of things that can be achieved with two-way entanglement. So this has more explanatory power because it can obviously do all this. And therefore, something which is not explainable like this is also not explainable from these. But it's not going to be the same when we compare the new and old definitions of non-locality. So the new definition for what I would call genuinely three-way non-local are the kind of things that you can't get with local operations, starting with two-way stuff. Two-way what? Quantum stuff? Yeah, but that would make it a difficult definition. Two-way non-signaling stuff? Yeah, but that also feels like maybe we're sort of prioritizing boxes, whereas we really want to be thinking about states. So I would argue that the correct definition actually be two-way generalized probabilistic theories. And so we can now define this and define tests for this. GPTs are the kind of side channels that Eric was referring to as like exotic beyond quantum. Vadim, you can think about these as quantum states with negative eigenvalues. But then they could give rise to negative distributions. So we'd say, no, not all quantum states with negative eigenvalues, only those quantum states with negative eigenvalues, which still yield positive probabilities when taken on an inner product with a product measurement. And so this would be like an entanglement witness. So if you replace quantum states with a set of entanglement witnesses, then what can you achieve? GPTs. And now I want to say, like, this is clearly a new definition relative to the old one. So Svetlichny in his 1987 paper gave an inequality for three parties. And he said, if you violate this inequality, then you are genuinely tripartite entangled using his definition. I haven't told you what that inequality is, but I can simply say if you take these Papeska-Rolich boxes that Eric introduced and just take three of them in parallel and combine them in sort of the intuitive way, which is you copy the settings and then you need to report a bit of outcome, but every party now has the outcome of two PR boxes in their lab, so they just do like an XOR. You get a distribution which doesn't just violate Svetlichny's inequality, it violates its the algebraic maximum. But this is clearly achievable with these two-way resources. So this is just to say, yes, you can do things with two-way resources, which relative to the old definition are genuinely three-way, but are obviously two-way by construction using a new definition. All right. So recap, the new definition, again, in terms of a causal structure, is if I can explain my non-local box by this kind of procedure, which there's GPT side channels, but only two-way GPT side channels, and shared randomness, then it's not genuinely three-way. How do I know whether or not my tripartite correlation is or is not tripartite non-local? Exactly the same idea of inflation, but instead of inflating a quantum state, we inflate the distribution. So now we would say, oh, if I could have achieved this tripartite distribution, then there would exist some six-partite distribution, which has similar features. Namely, if you look at the A1C2 marginal, it's going to be the same as that marginal, but now it's a classical marginal as opposed to a quantum state marginal. And we have the same symmetries, and we have the same notion of locality across various partitions. And now we could say, like, is there any six-partite correlation consistent with this? And the answer could come back no. And that would be a witness that the original thing could not have been explained by such a network, which is kind of convenient. So when we're asking about tripartite, genuine tripartite non-locality using this LOSR quantum network motivated definition, instead of being a semi-definite program, it's a linear program, which is even more efficient, very easy to do. We can get lots of these inequalities, and I'll give you one, and then I will close. So first I will point out, one might ask the question, okay, I've given you a definition for tripartite non-locality. Who is to say that nature is tripartite? Is there any quantum state which could be used to generate a tripartite distribution which would hit this new threshold? Because it's a new threshold, right? Just because there are genuinely tripartite quantum states doesn't mean that any of them could be used to achieve this notion of tripartite non-locality. So is nature genuinely tripartite non-local? Open question. Biologists solved this in 1977. except they weren't talking about non-locality, they were talking about the three kingdoms of life. So if we wanted to answer your question. Yes. So I mean, are the operational predictions of quantum theory such that they could give rise to something that would be genuinely tripartite? Which is to say, like, could we perhaps get away with a future theory, which would be a generalized probabilistic theory, but it would, in a generalized probabilistic theory, we would cover all of the predictions of quantum theory and maybe some more, but only using two-way sources? Or is there something that you would achieve which can't be explained with only a GPT two-way source? And so it turns out the answer is yes. In the interest of time, I'm not going to go through the argument, but I will point out that not only have we derived sort of inequalities, which if your tripartite distribution violates this inequality, then it means that you've achieved sort of this new threshold for genuine tripartite non-locality. But we did an experiment and confirmed that it can be violated. And it was shocking to me that when we put this paper out, like people that we didn't ask to do an experiment also did an experiment. So here, like, I think I'm an author of this paper. So there's an experimental team, and we said, okay, sure. Like, we wrote the theory paper. It's, you know, traditional that when you write a theory paper, you follow up with an experimental paper. But to my surprise, this definition caught on, and these people, I have no idea who they are, did the exact same experiment to show that you couldn't achieve this new threshold. And so did these people, who also I have no idea who any of them are. So that's nice. I will point out that if we compare new versus old definitions of tripartite non-locality, it's not a total order, which is different than we compared entanglement, because the new definition of things which can be explained two-way are things which can be achieved with two-way GPT resources. But the old Svetlichny 1987 definition of tripartite non-locality was things which could be expressed as combining one party off by themselves and the other two parties in communication. But two parties being in communication is a stronger resource than two parties sharing a GPT side channel. You can achieve more. But here you can use all three of them at the same time. Here you can only use one at a time. So, yeah. Okay. What's next? So I think in terms of these definitions that we're proposing, so you could certainly take a quantum network and certify that the network is good enough to meet those sort of like these definitions, which I think are well motivated from foundational principles of being genuinely three-way, genuinely four-way. But you could also use the same ideas to certify coherence in distributed computing, because you might have a processor which has nodes, and you could say, here is a process. Could I achieve it in any theory where there's only so many rounds of communication in the processor before it decoheres? So you allow for you know, a notion like of a GPT channel, which generalizes a quantum channel, and you can have it between nearest neighbors. And then you could, so now we're again in a theory agnostic form, and we could talk about the kind of correlations that you could achieve if your processors are connected in this way. And non-finite inflation as a general technique can be used to sort of provide constraints here and say, like, yes, your processor can pull off things of this threshold, and so on and so forth. So it's a way of benchmarking things which are not just small networks. So the last thing that I wanted to do is just summarize a few places to go look about more things, because what I've just said is a bunch of definitions and buzzwords and jargon, and it's like, what? I totally didn't follow half of that. So this is where you go to take it at your own time. This is a paper where we argued that it's important to have one resource theory, which to rule them all and in the darkness bind them. And we argued that if you're going to think about Bell inequality violation, the only sensible way to do it is to think about it in terms of local operations and should randomness. So there's a lot more going on here, but if you just read like the first 2 pages of this paper, it is a manifesto about how if you take physics seriously, you should use local operations and should randomness whenever you think about non-locality. Then we have this paper, which says, oh, that thing we said about shared randomness, if you want to connect entanglement to non-locality, which many people do, then you need to change the way you think about entanglement. So I had a slide up there which said you have these anomalies, like if you try to evaluate more versus less entangled, where you take LOCC as, if I could get there with LOCC, then this is better than that. And you use that as a way of pre-ordering your states, and you compare that to a pre-order of boxes, you don't get consistent results. And if you just think about states as ranking them in terms of what can be obtained from what with local operations due to randomness, all the anomalies go away, everything's very nice. And we propose here a definition for things which you can't achieve with two-way entanglement as a notion of genuine tripartite non-locality. It's different than the definition of genuine tripartite non-locality that I'm advocating here, because this is very much a not theory agnostic. It says assume quantum theory, but okay, it's well put together. This is a paper where we define our notion of whether or not a state is genuinely tripartite entangled. So we didn't want to use just genuine multipartite entanglement because that's a name that's been used before. So it's because this was inspired by network non-locality. We called it genuine network multipartite non-entanglement. We probably should have called it genuine LOSR multipartite entanglement, but I don't know whether APS allows us to use acronyms in titles. So it is what it is. And so it's called genuine network multipartite entanglement, even though I never actually call it that when I talk about it. But it gives you a nice introduction to non-finite inflation, defines the STP, provides these bounds, shows that GHZ and W states, for example, are, as you would think, genuinely tripartite entangled, and gives you some noise robustness around. And then we say, what if we wanted to think about quantum sources and prove that our distribution can't be achieved with two-way quantum sources? So the definition that I have generally been advocating does not presume quantum theory. I tend to prefer sort of theory agnostic definitions. But if you wanted to say, like, here is a distribution, it's tripartite. Could I have achieved it in a network with two-way quantum sources? Well, we give you a way to do that, which defines a semi-definite program, which is a generalization of the Navasquez-Peroni-Onestin, a hierarchy for understanding what's quantumly achievable in Bell scenarios. So this is what's quantumly achievable in network scenarios. Then we say, actually, we should provide a formal definition of multipartite non-locality, which is what I was trying to argue, which is it's genuinely three-way if you can't get there with GPT side channels, which are two-way only. And so this is a PRL, which is, I think, readable. It's like only 4 pages because that's the limit, which simply says, let's not go multipartite. Let's not try to like overly formalize and just give you a simple notion of like, here's what we mean by something which is genuinely three-way. It's not what people used to mean by genuinely three-way. And yes, quantum theory is genuinely three-way. And it has a sister article, which is in the PRA, which is any physical theory has to be boundlessly multipartite non-local, which to say that not only is nature genuinely tripartite, if you believe in the operational predictions, but it's also, it requires some 4-way, GPT resources, 5-way, any threshold you want, there's going to be an operational prediction of quantum theory that's going to require at least that and more. And this is the longer paper. It includes like a formal definition of things which are LOSR explainable with K-way GPT resources, and defines various forms of non-finite inflation when you go beyond the tripartite case. Okay. So that's pretty much it. I'll take questions. This is a QR code which just contains my email address. So if you copy this, you can say like, I want the slides. Can you send me these links? Because if you're just using your camera phone, it might be a little hard to find. So email me and I will answer whatever questions I can. But also ask now.
When you say, well, obviously, when you say noise stable, what are the rules on noise? Is it sort of like you say for a pure state? Are you allowing yourself to, like, what's the definition of noise? You're allowing yourself arbitrary perturbations to the wave function.
So I'm not sure like where you're referring to, like when I'm
at various points, you mentioned that something is multipartite and it's noise stable. And in the back of my mind, I assumed you meant that you take a state and you add some perturbation to it.
So let me try to answer, I think, in the best way that I can. So there were 2 notions of stability that had nothing to do with noise. So there was this idea of stability under parallel composition and stability under wirings. And that had nothing to do with noise. It just has to do with the fact that, like, if you define sort of a resource theory, which says like, this is what we call, cheap, this is what's expensive. then it should be sort of such that can you go from something cheap to something that's expensive by just doing either parallel composition or by doing sort of local wirings? If so, then there's a problem in your research theory. So the definitions that I proposed, like here, are stable under those concerns. In terms of stability under noise robustness, what you would want is to say like, it's kind of easy to define genuine tripartite entanglement for a pure state. We would expect that if you take that pure state and you consider a state which has very high fidelity to it in any direction, so it could be noisy, it could be pure, but slightly different, that these kind of small changes should not change it. That's intuitive. Maybe it could, but that would be a bit surprising. And so we do find that that's the case. So we find that not only is the GHZ state tripartite entangled relative to the definition, but we can show that states which have fidelity of, let's say, at least 80% with it are also all genuinely tripartite entangled. So
Okay, any additional questions? Okay. Let's see. Well, I have one which this is something that tends to bother me a little bit when people talk. Okay, so when I'm back in the days when I was phys rev editor, okay, and I would get things about general probabilistic theories, I would tend to have a very short fuse on those papers because, look, if quantum mechanics is going to be wrong, it's not going to be due to some general theoretical development, et cetera. It's going to be because some experiment doesn't turn out right. And so I was very skeptical of looking at the general probabilistic theories because, okay, is this, this criticism has been leveled at me in different directions. Is this mathematics or is this physics? Okay. And so, so your definitions are, yeah, I mean, you definitely like theory agnostic definitions. But I mean, how much would things change if you just limited yourself to, say, quantum mechanics? And so okay, classical versus quantum, as opposed to this larger framework of the general probabilistic theories.
yeah, so that's an excellent question. We know that so I could do like a defense that like GPTs are actually useful and we shouldn't forget about them entirely.
Okay.
But if you don't like them, which is fine, then I would say, yeah, you could say, let's just take a notion which is it's genuinely tripartite entangled if it can't be explained as coming from the kind of quantum networks where you have two-way entanglement and through assured randomness. And okay, that's your definition. We proposed that in a paper I have with David Schmidt and TC. And then this quantum inflation paper provides an algorithm which allows you to just check that. So if that's sort of the definitions you want to adopt, power to you, and we have the tools to do it.
Okay. Thank you. Yeah, this is just one person's opinion. Okay. Okay, any other questions? Okay, well, let's thank the speaker again.
Thank you.
I don't know, this lunch is not quite shown up yet. Oh, it's there. Okay.